Let's build a tiny GPT from scratch. Of course, you know about Chat GPT. So that word GPT, or I mean that acronym GPT is what we are considering right now. Building a tiny GPT from scratch. Our goal here is to build a miniature version of GPT completely from scratch while understanding every mathematical operation involved. So the learning objectives, by the end of this lesson, you will understand what GPT actually is, how autoregressive language models work, tokenization, embeddings, positional encoding, multi-head self-attention, feed-forward networks, layer normalization, residual connections, transformer blocks, training objective, text generation, sampling strategies, and how to implement a tiny GPT in Python using PyTorch. So that's what this is focused on. Now let's go. The first part is what GPT is about. What is GPT? GPT stands for Generative Pre-trained Transformer, basically. So, you know, the whole idea of transformer, talking about self-attention and all of that. So when you see ChatGPT, it's all about chat generative pre-trained transformer. So it consists of three fundamental ideas. First of all, you have the idea of generative. So GPT predicts the next token in a sequence. That's why it's generative. And that's where the idea of generative AI comes from. For instance, you impute, I love studying, and then the next prediction can come as mathematics, even on your phone, right? When you use your smartphone to some extent. So once you start, for instance, most of the times when I start typing my name, once I type my first name, my middle name and surname automatically just shows. So I just pick them instead of having to type them from the scratch. So thereby saving time. So that's the idea of generative. That's prediction, actually, by the way. So generation follows prediction. Then you have the part that is pre-trained. So generative pre-trained transformer. So for the pre-trained part, before performing specific tasks, GPT is trained on enormous text collection such as books, Wikipedia, research papers, and websites. The knowledge learned during pre-training is later adapted to downstream tasks. So how you get to do to how you get predictive stuff on your phone is that if you type a particular set of words constantly, so the phone then gets used to it. It learns your habit, the way you type, what you type, which word follows which word when you each time you type. So that's the pre-training in the context of your smartphone. But in the case of GPT, so a model is trained aforetime on books, Wikipedia, research papers, and websites, and all kinds of information that might be available. And then we have the third part, the transformer part, which we've talked about a little bit. GPT uses the transformer decoder architecture introduced in 2017. Unlike recurrent neural networks, RNNs, all words are processed simultaneously. Then attention captures long-range dependencies efficiently. Training can be massively parallelized. So we see generative pre-trained transformer. That is the full meaning of GPT. Now, the big picture is now this. The complete GPT pipeline is as follows. You have the input text, which is like what you can call your prompt, and that prompt is tokenized by a tokenizer that it is broken down into word chunks or into bits as much as possible. Then you have an embedding layer. So that's where you have the whole vector. You have numbers are assigned to the tokens and all that. You have a token ID, you have vectorization and things like that. And then position embedding to talk about the position each word occupies, and then you have a transformer block. So that's where the whole processing goes on. You have series of transformer blocks, layers and layers of transformer blocks. Then you have a linear layer. Then a softmax is now done on that. Softmax is what converts the attention scores for each word into probabilities and then predicted next token. So the next token is predicted. So once that is done, it goes again until the request, whatever request you have as your prompt is all answered. So each stage transforms the input into increasingly meaningful representations before predicting the next token. That's why you have multiple layers like that in between the prompting and the time the result is out. Now let's talk about step one, which is tokenization. So imagine you type something like you type a prompt, say anything at all. The history of caps, let's say. So then, since the computer doesn't understand English, it then converts those words. It breaks up the words, the history of caps. So it may be word by word or even chunks, portions of words broken up like that. So computers cannot understand text directly. So instead, every word or character is converted into an integer called a token. So example sentence, imagine you say, I love AI. So let's say each word now is taken to as a token. So I is assigned number 0, love is assigned number 1, and AI is assigned number 2. The encoded sentence becomes 0, 1, 2. So the computer does not understand I love AI, but it has been able to convert it to words that it understands. So it sees 0, 1. So once it sees 0, 1, 2, it can understand the relationship. So this numerical representation is what enters the neural network, and every other process goes on. Then we talk about character level tokenization. So instead of tokenizing words, we can tokenize individual characters. So for hello, for instance, hello then becomes HELLO. So H is a token, E is a token, L is a token, another L is a token, and O is a token. So in that case, you can have a vocabulary such that A is token 0, B is token 1, up to Z, which is token 25. So character level models are simple and useful for understanding GPT from first principles. Imagine you have the text, hello, and then the characters now, it's now sorted. So you now have to set the text like that. Then you then have story. So for C, you have I for I, C in enumerate characters. Then you have the itals, I C for C in story.items. So that way you break down the words. So then it's encoded. You have stoic for C in text. So if you print the vocabulary story now and print encoded, you have this. So vocabulary now tells you E is 0, H is 1. So everything has been arranged and numbered accordingly. So this sorting that you have here is sorting these words. So you have E is the first word, first letter, that is 0. H is the second one, that is 1. L is the second one, that is 2. Of course, there are two L, so L is L, so that's 2. Then O is 3. So if you now want to tokenize, so the encoded thing now, you have 10223 for hello, 10223 now becomes what that is, you know, numbered as. So having done that, we can then build the vocabulary. Supposing the training corpus is hello world, that is, you have trained the model already on hello world. So the unique characters are HELOWRD, because of course avoiding repetitions, and then of course the spaces. So the vocabulary size then is V equals 8, because you have 1, 2, 3, 4, 5, 6, 7 plus space. That means the vocabulary size is 8. So those are 8 unique characters you have in Hello World. So where V denotes the total number of unique tokens. So the vocabulary determines the size of the embedding matrix and the output layer of GPT. So those are the possible things that can be output. So step 3 now, you have the embeddings. One-hot vectors are sparse and inefficient. So instead, GPT learns a dense vector representation called an embedding. Suppose vocabulary size V is 6 and then embedding dimension D is 4. So instead of representing cat as 0, 0, 1, 0, 0, 0, 0, because you have vocabulary size 6, then GPT learns a dense vector such as 0.45 minus 1.1, 0.66, and 2.11. Now, these values are learned automatically during training. So the model takes care of itself, right? So when you train the model on whatever material you have available, so the model learns this pattern so that when you now prompt it, it follows this kind of patterns and it uses that to do all the whole matching. The mathematical definition of embeddings now, if V is the vocabulary size, that's the number of tokens. If you use letters or characters, that's the number of characters. If you use words, that's the number of words. If you use word chunks, so the total number of tokens gives you the vocabulary size, and D is the embedding dimension. Then the embedding matrix now is E as a subject of a V by D uh, real number system. So each token simply indexes one row of the embedding index. So if token I is encountered, X sub I is equal to E sub I, where E sub I denotes the ith row of the embedding matrix. So these embeddings are learned through gradient descent. So you have a simple example here. Imagine you have, of course, we are using PyTorch, right? Import touch neural network as NN. So the embedding now is NN embedding. Say you are embedding 100 by 32, and the tokens now for touch tensor you have 4, 8, 12. So the output now will be the embedding of the tokens you have. So that's 4, 8, 12 here. So of course, each 4, 8, 12 representing each each token, their token ID, so to speak. So then the output now you have the embedding of the token. So if you run this now, you then get something like this. You have a 3 by 32, you have a 3 by 32 token. So here the embedding is 100 by 32, but the tokens you have just three of them. So you have 3 by 32 like that. And then you end up having the uh the the outputs like that, giving you the embedding of that particular of the tokens you have here. So this is 3 by 32, right? So it means that this first set from here to here, that's one. So you have two, three, and it goes all the way down like that. Okay, or rather, it's 3 by 32, right? This is one, two, three, and then each of this now one, two, the five, we can just do this one, two, three, four, five times one, two, three, four, five, six. That's 30, then one, two. So you have this is uh one row with 32, 32 dimension 32. Second row with its 32, third row with its 32. So these are the three tokens with their embeddings now. Now, then we go ahead to talk about positional embeddings. Attention mechanisms have no inherent notion of word order, right? Therefore, GPT adds a positional embedding to every token embedding. Sentence, like that we've been playing with, I love AI, right? So I 0, love 1, AI 2. The final input representation is then xi equals ei plus pi. So ei is the embedding of each word, and pi is the position each word occupies, where ei is the token embedding and PI is the positional embedding. So putting the embedding of the token and the positional embedding of the token together, that can make more sense. So adding positional information allows GPT to distinguish between dog bites man and man bites dog. Because so that it won't just be like the sentence will mean the same thing to the computer if the position is not well articulated. Then you go ahead to talk about self-attention, which we've talked about a whole lot. The attention formula that revolutionized the whole of AI. So self-attention is the core mechanism that makes GPT intelligent. So instead of treating every word independently, each token asks which previous words are most relevant to me. And that happens because every word attends to every other word to know how weighty every word is to it. So to answer this question, every token computes three vectors. You have the query, what information am I looking for? You have key K, what information do I contain? And value V, what information should I pass to other tokens? So this similarity between queries and keys determines how much attention one token should pay to another. So unlike recurrent neural networks, self-attention allows every token to directly interact with every previous token in a single operation. So we have the attention formula, which I mean I've talked about it so much so that I won't even spend too much time on it. There's a whole video on breaking down the concept of attention and everything. There are a couple of videos, in fact. The attention mechanism computes attention as a function of query, key, and value, and then it is equal to the softmax. Softmax is the probability of qk transpose over dk. So qk transpose over square root of dk is called the scaled dot product, which actually gives the attention score. So that probability is then multiplied by the value. So Q is the query matrix, K is the key matrix, V is the value matrix, and D sub K is the dimension of the key vectors. So the computation proceeds as follows. You compute similarity scores using QK transpose, and you scale the scores by dividing by square root of dk to prevent extremely large values. Then you apply the softmax function to convert scores into probabilities. So multiply the probabilities by the value matrix to obtain the final attention output. That tells you the weight each token carries. Now, the question is why divide by square root of dk? As the embedding dimension increases, qk transpose can become very large. So large values cause the softmax function to become extremely peaked, leading to unstable gradients during training. So scaling by square root of dk keeps the values within a reasonable range and stabilizes learning. So it is basically for the purpose of stabilization. Now, suppose that a query is just to uh, single vector 2, the key is 4, and the value is 5. So to complete the attention scale, you have QK transpose. And since it's just they are just one value each, right? So you just have 2 times 4, 8. Then since there's only one token, so you compute the softmax of 8, which is equal to 1, 8. So e raised power 8 all over e raised power 8. That's what that is. And you get 1 here. And in step 3, you then have multiply by the value. So that's 1 times 5, and you get 5. Therefore, the attention given to the attention required here is 5. So, and then you can do that using uh PyTorch. So you have you import touch like this. Then you import touch neural network functional as F. So you have QKV with the 245 like that. So you have the scores, which is Q times K transpose. You have the weights, which I mean, this is just one in this case because it's the same, just one word. So at the end of the day, you have your scores. You have tensor score, that's 8. Attention weight is 1. That's the probability you get. And then you have the output tensor, which is 5 in that situation. So we can also have multiple tokens, right? So imagine the query is 1001 and the key is 1101 and the value is 5824. So if you compute KQ transpose, so K transpose, of course, K is 1101. So the first row 1, which is 1 1, becomes column 1. That's 1 1. Row 2 is 0 1 becomes column 2. That's 0 1. 0 1. So row 1 1 1 becomes column 1 here 1 1. Row 2 0 1 becomes column 2. That is 0 1. That's K transpose. And then we obtain QK transpose, meaning that if you multiply 1001 by K transpose, of course, if you multiply K transpose by a unit matrix, this is a unit matrix right here. So if it means QK transpose remains the same. So if you scale by square root of 2, because you have a 2 by 2 matrix, so you have two tokens in short. So each row represents a token, by the way. So here now, so it means you have square root of 2, which is 1.414. So if you apply softmax, you can apply softmax row wise. That means you get for each of these now, you have 1 over root 2, 1 over root 2, 0 over root 2, 1 over root 2, and you go on like that. So you do it row wise. Then in step 4, now you can multiply by the value matrix to obtain the attention output. This is precisely what ChatGPT performs. This is precisely what GPT performs billions of times during training. So it keeps doing this over and over again to give you your results. So you just see the answers coming, but a lot of mathematics has gone on in the background. So you can import math, import touch.nn functional as F. So imagine the query using PyTorch now. You have 1001. The key is 1101 and V, the value is 5824. So the scores can then be computed as Q multiplied by K transpose. Then the scaled scores can then be scores over square root of 2. You get square root of 2 from the from not from math, right? So, and then the weights now, you then do the softmax F. So the softmax is coming from the functional. The functional we had mounted here as, this functional as F. So you can get softmax function from that. Then you can have the scaled scores in dimension -1. So the output then is weight multiplied by V. So you can print the scores, the scaled scores, the attention weights, and all of that. So when you do all that, you then get so you have your values. So you have the scores 1011, it remains the same. That's QK transpose. And then the scaled scores, and when you divide through by square root of 2, which is 1.414. So you get 0.701, you get 0 here, you get 0.701 here, you get 0.701 here also. Then the attention weights now, talking about the attention weights, you do the whole softmax thing, so that'll be e raised power this, e raised power each of them in short, and then you now divide each of them by the total of everything. So you get 0.6698, 0.3302. I mean, you do it row by row because each row is each row is actually uh one token. So you do it token by token, such that but when you add this and this together, you get one. When you add this and this, you get one. That's how it works. So then the final output, now you multiply this by the value. The value is this 5824. So you multiply this 2 by 2 matrix by that value, and then the output tensor is 409866.6790, and then you have 356.0. So it means the first token seems to carry more weight because the output values for that for the first row are actually higher. So you then have the multi-head attention. Instead of computing attention once, GPT computes attention multiple times simultaneously. So each attention mechanism is called a head. So different heads learn different relationships within the text. For example, head 1 can learn grammar, head 2 can learn pronouns, head 3 can learn long-range dependencies. That is how the first word connects with the 1000th word or some or whatever it is you're considering. Then you have head 3 can learn long range dependence that head 4 learns semantic meaning. So each head produces its own output. So these outputs are concatenated and projected back into the embedding space. Then we have the mathematical formulation right here. So mathematical formulation for multi-head attention. So suppose there are H attention heads. So each head computes head I, which is attention for query I, query key I and value I. The outputs are concatenated. So you have multi-head QKV equals concatenation of head 1 all the way to head H multiplied by W0, where W0 is the output projection matrix. This allows the model to capture multiple types of relationships simultaneously as different heads has learned different things. Then we'll talk about the feed-forward network. After self-attention, every token independently passes through a small neural network. So the architecture is like this. You have linear, you have GALU, and you have linear again. So unlike attention, the feed-forward network processes each token independently. So its purpose is to increase the expressive power of the model. So you have all this kind of thing now. So passing through these neural networks, or what we call you can call some kind of activation function. So look at this now. You have the feed forward. Okay, I mean, this is our first time of coming across GALU. So we know ReLU, we know GALU. So let's quickly establish the key difference between ReLU and GALU. ReLU versus GALU. ReLU versus GALU. Like this. So here, ReLU is rectified linear units, which is simply the maximum value of 0 and any value you bring to it. The bigger of them is the result. Then GALU is Gaussian error linear units. This is rectified linear units. So this is Gaussian error linear units. And they are non-linear activation functions used in neural networks. So ReLU uses a hard cutoff at 0. So maximum of 0 and x is what you need. Then offering high computational speed and sparse representation. But GALU weighs inputs probabilistically using a smooth continuous curve, avoiding dead neurons, and improving performance in deep language models like BERT and GPT. As ReLU means like rectified linear units, while GALU means Gaussian error linear unit, like that. So this is us coming across that. So that's the neural network that's more like the activation that's happening there. So its purpose is to increase the expressive power of the model. That's the work of feed-forward network. Now, talking about feed-forward equation now, the feed-forward network computes the feed-forward network of X to be W2, then an activation function that takes in the first weighted sum of which is W1X plus B1, then adds that to another bias. So because this is first weight and it's bias, so it forms a weighted sum or linear transformation, if you like, or linear combination. Then you pass that through an activation function sigma. So whatever you get, it now becomes your new input multiplied by the second weight added, and all of that will be added to the second bias. So W1 and W2 are weight matrices, B1 and B2 are bias vectors. So sigma dot is usually the GALU activation function. That's the Gaussian error linear units. So uh did I say is that Gaussian error linear unit exactly? That's GLU. So this is usually the GALU activation function in GPT model. So you throw this linear transformation into the GALU activation function. So the first linear layer expands the embedding dimension. Then the second linear layer projects it back to its original size. So you have something like this happening there. So using PyTorch, so you have the feed-forward network feed-forward network. So you have the sequential NN linear 64 by 256, NN GALU, then NN linear again 256 by 64. So you have this linear, you pass it through GALU and you take it back to the linear. And that's exactly what's happening here. So you have a linear expression here, then you have the activation function, which is non-linear, and then you take it back here and you get your linear back like that. So you have 64 by 25, 65 by 64. So if you have an input that is 3 by 64, you end up getting 3 by 64 like that as your result. So why use GALU instead of ReLU? I mean, we've been talking about ReLU all this while. So modern GPT models use the Gaussian error linear unit GALU, the GALU activation function. Unlike ReLU, which is the maximum of 0 and x, GALU smoothly weights inputs according to their magnitude. So magnitude is involved here. So A commonly used approximation for JLU of X is 0.5x into 1 plus tanh. Tanh is a kind of saturation function, not like the proper sigma function we've been seeing. So tanh of square root of 2 over pi into x plus 0.04715, 0.044715 x cubed. X here is the input, like we know. So this smooth activation generally leads to better optimization and improved language modeling performance. So now we see Gaussian error linear units being so useful. Then we have residual connections at step 8. That's the steps we saw, explaining them one after the other. So step 8 now, training very deep neural networks is difficult because gradients can become very small as they are propagated backward through many layers. So residual connections solve this problem by allowing information to bypass individual layers. So instead of computing output equals layer X, GPT computes output equals X plus layer X. So the original input is added back to the output of the layer. So this simple idea allows gradient to flow more easily through deep networks, making training significantly more stable. Now, why residual networks? Why are residual networks important? Suppose a layer computes f of x. Without a residual connection, the output is simply f of x easily. But with a residual connection, you have h of x to be f of x plus x. Even if f of x is approximately 0, the information from the original input is preserved. So benefits include faster convergence, improved gradient flow, easier optimization, and deeper transformer architectures. Those are the works of residual connections, residual connections, yeah. So, and then we have layer normalization now. So deep neural networks often become unstable because the activations can vary significantly between layers. So layer normalization standardizes the activations for every token. So given an input vector x, which is x1, x2 up to xt, its normalized version rather is x cap, which is x minus mu over square root of sigma squared plus epsilon, like that. So mu is the mean of each of the of all the x's. Then sigma squared is the variance of all the x's, and epsilon is a small constant for numerical stability. So imagine you're taking, say, the log of 0, so that'll be undefined, but if you have a small value there, it will make sure that you don't go to the values does not the value does not go to 0. So after normalization, GPT applies learnable scaling and shifting parameters y equals gamma x cap, the x cap we have here, plus beta, like that. So, and that will happen for all the d dimensions, because this will be x1 minus mu over this, x2 minus mu over that, and so on and so forth. And then you have gamma x cap plus beta. Now, why layer normalization? So layer normalization provides important benefits like faster convergence, more stable optimization, reduced sensitivity to initialization, improved gradient flow, and better training of deep transformer models. Unlike batch normalization, layer normalization does not depend on the batch size. This makes it especially suitable for transformer architectures. So imagine that you have the whole layer thing here. So layer normalization, you have layer num of layer num 64, and then your x is 5 by 64. That's your input. You have a 5 by 64 kind of token. Then y, which is layer num of x. So you can, if you print the shape, you see it ends up giving you the 5 by 64 as expected. So then you can have a transformer block. A transformer block combines all of the components studied so far. So you have the inputs, you have the layer normalization, you then have masked multi-head attention, then you have the residual connection, you have the layer normalization, you have the feed-forward network, then you have residual connection, and then you finally get an output. So everything is now put together at this final phase of the transformer block. So each transformer block lends increasingly sophisticated representations of the input sequence. So modern GPT models simply stack many of these blocks together. So you then have mathematical representation. Suppose the input is x. So the attention sublayer computes x prime to be x plus attention layer num x. And then the feed-forward sublayer computes y equals x prime plus FFN. That's the feed-forward network of layer num x prime. So the x prime you have right here. So the final output of the transformer block is then y. So attention layer x prime. So you have x plus attention layer num x. So this x prime now is thrown into the feed-forward sublayer, and then you get y, and then the final aspect of the block is this y you have here. So this structure is repeated many times throughout the generative pre-trained transformer model, which GPT means. So you have a mini GPT architecture here. A complete Tiny GPT model will consist of input tokens, those are your prompts, then token embedding, positional embedding, transformer block, another transformer block, layer normalization, linear layer, softmax, and next token prediction, like that. Once the softmax is used to compute the probabilities, the token with the highest probability is naturally generated, except you now involve something like temperature that calls for creativity or variety. So every transformer block refines the representation of the sequence before the final prediction layer produces probabilities over the vocabulary. So talking about the output layer now, um, suppose the vocabulary size is V. The final linear layer maps each embedding vector X in the D-dimensional real number system into Z belonging to RV, where Z is WX plus B. So each component of Z is called a logit. So each component of this is called a logit. So these logits are converted into probabilities using the softmax function, which we've seen a couple of times. So coming to softmax again, the softmax function converts logits into probability. So given logit Z equals Z1, Z2 up to ZV, the probability assigned to token I is then Pi, which is the exponent of each of the Z's all over the sum of all the exponents. So the resulting probability satisfies 0 less than or equal to Pi less than or equal to 1, which makes sense because probabilities should not be lower than 0 or greater than 1. Then, and summing it all up, you get 1. So GPT predicts the token with the highest probability or samples from this probability distribution like that. So, um, we have this happening here. Imagine we use PyTorch again. So import the functional because we need softmax from there. So you have the logits, which is given, normally we would usually use NumPy arrays, but here since we are using PyTorch, PyTorch deals with tensors. So of course this is still an array, but it's not like a tensor using PyTorch. So imagine you have Z values. Z1 is 2.1, Z2 is 1.3, Z3 is 0.4. So the probabilities then are computed using softmax. So softmax just automatically takes in the logits in dimensional -1. So that means e raised power 2.1, then e raised power 1.3, e raised power 0.4, you get the values. And then to calculate the probabilities, now you have e raised power 2.1 all over e raised power 2.1 plus e raised power 1.3 plus e raised power 0.4. And you do that for each of them. So by the time you are done doing all of that, so you get the tensor. So I mean, you now get the probabilities. So for 2.1, the probability is 0.617. For 1.3, the probability is 0.2753. For 0.4, it is 0.1119. So that means the first one is the one that requires the highest attention. All right. So of course, when you add up all of this, you should get one because it's now a probability distribution. Then we have the loss function. So GPT learns by predicting the next token in a sequence. So example, input I love, and then the target is there. So the model produces probabilities for every token in the vocabulary. Then the quality of these predictions is measured using the cross-entropy loss. So if he doesn't get it right, like the loss helps us to know what has been predicted correctly or not, or how far what has been predicted is from the reality that is expected. So cross entropy loss. Now, suppose the true probability distribution is Y and the predicted probability distribution is P. So the cross entropy loss then is L equals minus summation of over I of yi log P. I mean, we've dealt with this a couple of times. So I think there's a whole video dedicated to loss. So since the target token is represented as a one hot vector, this simplifies to L equals minus log P of the correct one. So lower loss indicating better predictions, right? So training seeks to minimize this loss over the entire data set. So from the first prediction, so this loss is made smaller and smaller until the desired point. So imagine, we have logits 2.3. Logits are all those the Z values, right? So you have 2.3, 0.4, Z 1.5, and then the target. So you are targeting 0. So if you now so compute the loss now. So you have to do F. So softmax and cross entropy comes from the PyTorch neural network functional F. So you have F dot cross entropy. You take the logit with respect to the target. At the end of the day, if you print the loss is 0.4693. So that may be high. If you keep fine tuning, you may end up getting something better. So for the sampling in step 13, after training, the generative pre-trained transformer generates take text one token at a time. So the generation process is like this. You have the current context, and then you use the model on it. logits are generated from the model. The logits are converted into probabilities using softmax. Then you have a probability distribution. Then you sample the next token based on whatever method you have chosen. If you use the greedy algorithm, it means the token with the highest probability is automatically selected. So you add that and then you repeat the process. So each newly generated token becomes part of the input for predicting the next token. So this auto-regressive process continues until the desired sequence length is reached like that. So example, predicting the next token here. Suppose the training corpus is hello world. Like you have trained your model on hello world, right? So the current context is now hell. So the model automatically predicts that, oh, based on what I've been trained on, after hell it should be O. So you have O. So the context is now updated to hello. So the next prediction will now be space because what's that? It's length, there was space in between. And then the next context, the model then continues predicting W, then O, then R, then L, then D. So by repeatedly predicting one token at a time, GPT generates complete sequences of text. And that is exactly why you have, when you prompt ChatGPT or any GPT-based model for that matter, you don't get the results in one blow. The results come sequentially because of this behavior. So we now want to build a tiny GPT, right? We now implement a miniature GPT model from scratch using PyTorch. So our implementation includes character level tokenization, token embeddings, positional embeddings, masked self-attention, multi-head attention, feed-forward networks, transformer blocks, training using cross-entropy loss, and also regressive text generation. Although much smaller than GPT-2 or GPT-3, this model contains all the essential components of modern GPT architecture. So this can give you a sneak peek into what is going on in the old chat GPT model. So before running the model, we need to create the input text file with some text data. This text will be used to train our tiny GPT. So this is me creating the input text here. So create a dummy input text file for demonstration. In a real scenario, this would be a much larger data set. This is something very simple just for the purpose of demonstration. So you have an example text here. Oh, wonder, how many goodly creatures are there here? How beauteous mankind is. Oh, brave new world that has such people in it. This is our own text here, for training the GPT we are building, the tiny GPT we are building. So, and then we call it input.txt. That's the name of this file. So then if you print created, so once it is done, it just says created input text with example text. So I do that now. So it does. So by running this now, this text has been created. This is the corpus for training our tiny GPT that we want to create. So the next thing we now do is so using PyTorch, right? So we need the neural network and we need the functional. So let's say we have hyperparameters, batch size 16, block size 32, maximum number of iterations, we have 3,000, evaluation interval is 300, then the learning rate is 10 raised per minus 3. So the device is CUDA. If touch CUDA is available, else we use CPU. So CUDA is default, if not, we use CPU. Then number of embeddings is now 64. Number of heads, that's learning heads. Attention heads, right, is 4. Then number of layers is 2, and then the dropout is 0.2. So if you read the training text now, so with open, so this in this next line, in line 22, 223, we want to read that text that we had created, this text created up here now, that thing looking like poetry. So to open that, we'll say with open input text R encoding UTF-8 as F, then text is F read. So this is the two lines to read that document. Then we can build the vocabulary now. So we have characters. So first is sorted, like all these characters are sorted, and then we now set the text. So we have vocabulary size talking about length of the characters now. And just like what we did before now, you have story for character now, you have I for I for every character in the numeric characters. Then for the itals, you have I, CH for I. So the characters for I for CH in the numeric characters. Then you encode the lambda, you have S stoic for C in S, and then lambda L. So then you have the data. So you have the data here. So you then training and validation split now. So we have the whole training and validation for standard machine learning processes. So don't forget to run this so that it can be committed properly. Now, if you need more explanation on this whole code, you may want to, take time to look at it line by line. Then training and validation split. So n is integer 0.9 times length data. So training data now. So the training data is everything from the beginning up to 0.9 of the length of the data. And then the validation data is the rest from n up to the last, like that. So it's more like if you have 100 characters, 100 characters in the text. From all the conversions we've done, the vocabulary size there talks about the number of characters. So if you have 100 of them, so it means from 0 to 90 will be used for training, and then from 91 to 100 will be used for validation of the data, like that. So, okay, have I run that? Did I run it? Let me see. Let me just run it to be sure. Okay, that's done now. So that step is done. Then we can then create from still on the same thing, we can create mini batches. So instead of processing the entire data set at once, GPT trains using mini batches. So each mini batch contains an input sequence of length block size, which we already set up here. So the whole block size thing, and then, 16 and all that. So that is used batch by batch. So the corresponding target sequence shifted by one token. For example, inputs, if you input hello world, then the target is hello world, right? Like that. So the model learns to predict every token simultaneously. So here now you define get batch split, data is train data, if split is train, else validation data. So you have IX to touch random integer, length data minus block size, then you have batch size, then X is talk stack and all this going on like that. So we have to do that. So this helps us to learn to predict every next token simultaneously like that. Then building one attention head. An attention head computes queries, keys, and values, attention scores, softmax weights, and weighted values. So each head learns one type of relationship in the text. So GPT uses several heads simultaneously. So in this case, now to create attention head, we come to this place. So you define initialize, you have self head size super. So it means that there's a super, there's a function inside a function here. That's why you have this super thing. So you have the self key NN linear, then you have the number of embeddings, the head size and the bias. Then you have all of this. Then you also define a function forward. That's BTCX shape and all that for the KQ and the weights and all of these things right there. Should I make this bigger? So, so for the function up to the attention heads now, you have this part here up to self dropout here, and then for the second part, you have another function forward, BTC X shape. You have the key, self key, query, self query, and all that. Then you have the weight. That's QK transpose that we are used to, and you have the weight, all of that like that, and then you then have the softmax. I mean, that's the whole process going in training our own Tiny GPT like that. So I run it, and then we have that. So you're not seeing any result yet, right? Now this okay, okay, this has to go because this is not necessary anymore. This goes. Now, so I run that. So why do we use a casual mask now? So we have a masked field here. So you may be wondering why do we have to use a casual mask? So GPT must never look into the future during training. So GPT is not worried about the future because that's to learn it. We are still training it. So suppose the sequence is I love AI. When predicting love, the model is allowed to see only the I before it. So it's not supposed to see the AI coming after. So when predicting AI, the model is allowed to see only I love, right? So the lower triangular mask ensures that future tokens are hidden during attention computation to avoid, information seeping. It's more like a student seeing the question before an exam. So that, that's not allowed. That's the kind of thing that happens. That's why masking, a causal mask is used, like we have right up here. So you have the causal mask like that. Now, I said I called it casual mask the other, it's causal mask. So the lower triangular mask ensures that future tokens are hidden during the attention computation. So this property makes GPT an autoregressive language model because it's whatever prediction it's making is strictly based on what has been before it, not anything in the future. So the causal mask is a lower triangular matrix like this. So it has ones all on the principal diagonal and everything below, then everything above is zero. So entry contains zero. Entries containing zero are replaced by minus infinity before applying the softmax function. That's e raised per minus infinity, so that it can then still end up being zero. So consequently, e raised per minus infinity is zero. So future tokens receive zero attention in that regard. So imagine you have mask touch dot trill touch once you have a 5 by 5, so it can have this mask 1 1 1 1 like this. So if you make it 10 by 10, it also follows suit. So you have 10 by 10 like this. So you have the same thing for 10 by 10. So let me take it back to what it was, 5 by 5. So we have this. So talking about multi-head attention now, instead of using a single attention head, GPT uses multiple attention heads so that different attention heads can learn different things like grammar, like syntax, and things like that. So instead of using a single attention head, GPT uses multiple attention heads. Each head learns different linguistic patterns. After every head computes its attention output, the results are concatenated and projected back to the embedding dimension. So we have the multi-attention thing here. So we have two functions. So define in it, you have initialize this, you have the self, the number of heads, head size. In case you're wondering what this whole thing is about, you can check my playlist on Python basics. So there we talked about Python functions, how to define functions in Python. So that's you defining your particular function. So these are functions being defined here. So you have self as end module list and all of that. Then self project, all of that. Then you define the feed forward function, I think. So you have all of this here for the multi-head attention uh like that. So the class, so here we are actually, this is actually something about object-oriented programming. So you create a class here. So you also go to see Python classes. We check my playlist on Python basics like this. So don't forget to run it because so far we don't have any results. Okay, this one has to go too. This goes. So we've run this. Then we have feed forward network. After attention, each token passes through an independent neural network. The network consists of linear layer, the Gaussian error linear unit activation, then you have the linear layer again, and then you have a dropout. So the embedding dimension is first expanded and then projected back to its original size. So for the feed forward now, you have the code right here. So you define a class, feed forward, NN module. So under that now, you have, so this is more like this whole idea of a function inside another function. So things like automorphism and different concepts like that that you see under object-oriented programming in Python. Then so here you have this definition forward again for the feed forward like that. So I run this also. So we are building up our Tiny GPT gradually. So talking about transformer block now, a transformer block combines all the components you have studied so far. So it consists of layer normalization, masked multi-head attention, residual connection, layer normalization, feed-forward network, and residual connection again. So this is the fundamental building block of GPT. So modern GPT models simply stack many transformer blocks together like this. So now we have can I see everything at once? Okay, we can do it step by step. Okay, this is also meant to be gone. So you have this whole thing for the feed forward. I mean, for the transformer block like that. So another class defined class block and then module, then is then define two functions inside there again. So everything we explained manually before. You remember the other time you have x equals x equals x transpose equals x something something. Then you now have x again. So it's more like the whole updating, and then it finally returns the x here. So understanding the transformer block, suppose that the input is X. So the first layer normalize is applied. So you have first layer normalization. So you have layer norm of X. Then the normalized representation is processed by a maxed multi-head attention. So you have A now, which is attention of the layer norm X that you had before. So this residual connection produces X prime, which is X plus A. So this A now comes here. So everything you get at a stage goes to the next level. So this X prime now, you then have the feed forward network layer norm X prime. Finally, you then have Y, which is X prime plus F. So the output Y becomes the input to the next transformer block. So it's passed on like that until you get where you need to get. So finally, let's build the Tiny GPT model we have been working towards all this while. So the Tiny GPT model then contains token embedding layer, position embedding layer, multiple transformer blocks, final layer normalization, then linear prediction head. The prediction head produces one probability distribution over the vocabulary for every position in the input sequence. So we then have this now. So you now define a class, Tiny GPT, NN module. Then you have, now this is based on previous functions. Anytime you see super like this now, so you have it's referring to other functions in the process. Then you have the whole self-position embedding, token embedding, position embedding here. So based on this is self token embedding is based on vocabulary size and number of embeddings. Position embedding is based on block size, like that. And you have self blocks here. Um, so using NN sequential block for all the range in the N layer, then you have the NN layer norm, like that. Then you define the forward feed forward. So talking about so you have token and position, cell block, you have the logits, you have the loss. If the target is none, if the target is none, right, until the loss becomes none, we keep going. And then finally, once all of that is done, you then return the logits and the loss to know how close you are to your expectation. So this is like the tiny GPT part. Then but that's not all. Then we still have other functions here. You have I hope I'm not repeating this though. Return logits and loss. So once that is done, then you still go on, let's say, um target none. Hope I'm not putting the same thing here. This is BT. Okay, that's BTC. Now this is BT alone. So another layer, another layer. We have this here. So now, so far, no result, right? But we are building up towards something. How the forward pass works. Given an input sequence x1, x2 up to xt, the model performs the following steps. It converts every token into an embedding, add positional embeddings, pass the sequence through several transformer blocks, apply layer normalization, compute vocabulary logits, compute cross-entropy loss during training, and during inference, only the logits are needed for text generation. So the logits are then converted into probability, right? So how do you initialize the model? So once the model architecture has been defined, like all we've been doing, we create an instance of the network and move it to the selected computing device. So if a GPU is available, training will be considered considerably faster. So now, you call that GPU. So more, this GPU function we just defined here. So this one up here. So we call this the tiny GPT. We call that. So we have model is GPT dot to device, then you print the model. So when you print the model now, you get all these plenty things. So you have tiny GPT, token embedding 29 by 64, position embedding 32 by 64, block sequential, zero block, multi-head attention, module list, all those things we've been doing now. So the whole linear GLU, linear dropout, blah blah. So everything has now been stacked together here like this. So and then we can talk about optimize. So this is initializing the whole GPT model. So this is also initializing that. Then we then have the optimizer. GPT is trained using the Adam W optimizer. So Adam W combines adaptive learning rates, momentum, and weight decay. So these properties generally lead to faster convergence and better generalization than standard stochastic gradient descent. So in this case, now if you talk about the optimizer, so you have touch.optim.adamw. So you have the model parameters and the learning rates which you already defined before. So this takes a little bit of time for this whole optimization thing to happen because it's like fine-tuning the process. So that's done now. And then we go for the training loop. Training consists of repeatedly performing four steps. Sample a mini batch, compute predictions, compute the loss, update the model parameters using gradient descent. And these steps are repeated thousands of times until the model converges. And that's exactly what these codes are doing. Okay, I did it before, so I just want to do this again and see how far it goes. So uh, we are training the loop by sampling a mini batch, computing predictions and computing the loss and updating the model parameters on using gradient descent until we get an acceptable loss. So step 0, loss was 3.4882. Step 200 now 0.2931. So it's dropping. Step 400 0.1093. Step 600 0.0707. 800 0.797. Okay, this leading to a bit of fluctuation. So it's been dropping, then this one goes now, it's finally dropped better. So you have 0.0629. So we keep going. So we keep computing the loss until we get an acceptable level of loss. So if zero loss is what we need, we keep going until we get there, or until we get something really close. So now you can see 0.629, 0.540, but then it's increased again, but now it has dropped to 0.544, like that. So that's the process of the training loop now, to be sure that we have an acceptable level of loss. So step 2000, you have loss 0.0513. So you can see it's grew ahead of this. So this one increased also. So it's kind of unstable. So this one has also grown big. But I mean, that's the whole training process going on. And now this one has dropped to 0.424 now. And then we keep going. So at level two, step 2600, that's 0.570, which is bigger than what we had. So it's like there's a kind of instability happening. So of course, for bigger models, these things are well taken care of. So at the end of the day, the final loss we end up getting is 0.0619. So now the question is, what happens during backpropagation? Of course, remember the process of backpropagation. We have forward propagation, which leads to a prediction, and then backpropagation, which leads to training, that is modifying, comparing what is predicted with the reality to compute loss, and then to make the loss lower. And that's the process of backpropagation. So after computing the loss L, PyTorch automatically computes the L, the theta for every parameter theta in the model. So the optimizer then updates every parameter according to theta equals theta minus eta dl d theta, which is the gradient descent, where eta is the learning rate rather. So repeated parameter updates gradually improve the model's predictions. So, and then we talk about monitoring training now. So during the training, the cross entropy loss should gradually decrease. Now you can see what we have here is not the ideal case because it's fluctuating. We already have something less than 0.619, but the final step was 0.619. So I mean, in the ideal situation, we probably won't get something like that, but that's just to demonstrate what the whole thing looks like. So during training, the cross entropy loss should gradually decrease. So for example, you have step 0, loss can be 4.87, and by the time we get to step 1000, it's now 1.51. That's ideal. But what we saw in our case was you have the loss, it will go down, it will rise up, and all of that. So a decreasing loss indicates that the model is learning meaningfully statistical patterns from the training data. Now, because our training data is very small, that's probably why this loss here, it's oscillating, it's not stable, so it goes up, it comes down, and all that. So normally it should go down all the way. So and that's because our training data is not that robust. So that's one reason that can be. So that, and I think in the previous video we already talked about the fact that to get why big AI models suddenly become smarter, it's because we can fine tune things like the model size, which is based on model size based on parameters, and then you talk about the training data, and of course the model size, training data. I think there's a third thing which I'm not remembering right now. Training data, model size, and compute. Yeah, that's computational resources available. So talking about generating text now, after training, so we have trained the model now. Of course, based on the data we have at least, and we saw that the loss is not that reliable. But I mean, it's something. So if you have better text, you get better results. So after training, the model can generate entirely new text. So generation begins with a short prompt called the context. Or yeah. So example, once upon, if you start with that, don't forget what we had originally, right? The original text that with which we started this whole story. Where is it now? I hope it's not too far away. I think it's far off. Uh, okay. Okay, I think I've left that place. Okay, if I don't find it, I'll just keep going. So that text that was looking like poetry. Okay, if I don't find it, I'll just go on. Yeah, this text right here. Where is it now? It was created here. So, oh, wonder how many godly creatures are there? Blah blah blah. So there's nothing like once upon a time in that, by the way. So let's see what happens. Uh, uh, okay, let me memorize something here. So let me just say how many. All right, I'll think of how many, but let's see what happens with once upon a time. Let's see what it does with that idea because it was trained on that text. So when we go for how many this time, let's see how that does work. Um, okay. Yeah, so now you now have generated text. Did I run this now? Oh, Okay, yeah, once upon. So the model predicts the most likely next token. When you start with once upon, the predicted token is appended to the input, producing a new context. So this process repeats until the desired text length is reached. Because GPT predicts one token at a time, it is called an autoregressive language model because every new word produced, new word generated is going to be based on the previous words generated. So at touch, no grad now. So define generator, we have model start text, new maximum new tokens, you have 200. So model evaluation, you have IDX, Stock tensor, and all that. The whole loss, the probabilities to know which next word should be and everything. So we have all of that here. So imagine the generated text now is now generate model once upon. So maximum of new tokens, you have 300. So print generated text. So if you run this now, so you have once upon. So you now have once upon is oh brave new world. So you see, it's related to all of that because there was no once upon in that thing. So that has such have unkind. So it's really not making sense because number one, the text is not that robust. But let me change to how many and see what happens. How many? So if I do how many, which is actually in that text, see what happens now. So how many godly exactly? So you can see it's this one is now looking more like some of the things we saw there. So how many goodly creatures are there here? How beauteous mankind is, oh brave new world that has such are there here. How beauteous mankind is. So something like this. So we have this. So and each time the reason why you get different results, why each time you prompt ChatGPT is because of the probability that is going in the background. So imagine, let me go and say mankind. Let me just start with mankind. Mankind. So that now, okay, it's giving error because mankind is not part of what it is trained on. So I have mankind, yeah. So it is case sensitive. Mankind is oh brave new world. So mankind, so it means it follows mankind for the most part. So let me say beauteous mankind and see what happens. Beauteous, beauteous mankind. Let's see what that looks like. So it says beauteous mankind is oh brave new world. So you can see it's giving things related to the original text on which it was trained, how beauteous mankind is, something like that. So that's how all of that goes. So how text generation works. Suppose the prompt is the sky is, the model computes a probability distribution over the vocabulary. We've talked about it a lot of times. So blue 0.63 probability, clear 0.14. So you have a probability distribution and following greedy algorithm just picks the highest probability word. So the sky is blue. So one token is sampled from this probability distribution. So suppose blue is selected, the new context becomes the sky is blue. So this process repeats until the desired number of tokens has been generated. And then we have sampling strategies. So different sampling strategies produce different styles of text. So you have greedy decoding, of course, that's what I've been talking about all along. So always choose the token with the highest probability. The advantages is that that is fast and deterministic, but disadvantage it is often repetitive and less creative. So that talks about that's where the idea of temperature comes in at some point if you want creativity. So for random sampling now, randomly sample from the probability distribution, then advantages this is more diverse and more creative. Then disadvantages may produce less coherent text. And that's why you can see some of the text generated here, they don't really make sense. So beauteous mankind is exclamation, oh brave new world. That has such have unkind blah, blah, blah. So that's what is happening right there because of create the GPT trying to just pick things randomly. Then those are some sampling strategies we know. Then you also have temperature sampling. So temperature sampling creates allows for creativity and variety in text generated. So text controls the temperature controls the randomness of text generation. So given logit Z now, temperature modifies the probability distribution as this now. So you now have Z1 over T. All right. So that shifts instead of having the probability always big or something. So the temperature like tries to help to reduce the probability of predicting certain words so that there can be fair distribution. So if the temperature, for instance, is less than one, so temperature less than one produces more deterministic text. So you always get the same kind of text. Temperature equals one uses the original probability distribution. So whatever you have, it gives you like that. But when the temperature is greater than one, it produces more diverse and creative text. So if you want diversity, you want temperature greater than one. But temperature less than one gives you something that is more determined, things with higher probability. So T equals one uses fair distribution of what you have. So typical values now will be temperature 0.7 is a good example of less than 1. Temperature 1.0, of course. Then temperature 1.2 is greater than 1. So higher the temperature, the higher the creativity. That's the deal here. So instead of computing these the the softmax uh, based on just exponents, but you have exponent z, it's now be exponent z over temperature. So imagine you have a temperature of 0.8 and then you have logits. Now logits over temperature, then you now calculate the softmax of the new logits that has been divided by temperature. So that calls for better creativity. So we can have a mini project. So you can then build your own Tiny GPT text generation. So you follow the same steps. So build a miniature GPT model capable of generating text from a custom data set. So you have the suggested workflow. Select a text corpus, build a character level vocabulary, encode the text into tokens, and create training mini batches. Implement token embeddings, add positional embeddings, implement max multi-head attention, build transformer blocks, and train the model using cross-entropy loss, then generate new text from a user-friendly prompt. Although small, this project contains all the essential components of modern GPT model. So if you understand what I've done in this video, you'll have an idea went into ChatGPT. The only thing is that that is more robust, right? So this is why we call this one a tiny GPT. So after your tiny GPT is working, try the following improvements. You can increase the number of transformer blocks. You can increase the embedding dimension. You can increase the context length, increase the vocabulary size, replace character level tokenization with subword tokenization. So instead of having character, you have what's broken. Then you can train on Shakespeare, train on news articles, train on mathematics textbooks, train on your own writing, compare different learning rates, compare different batch sizes, compare different temperature during text generation, observe how each change affects training speed and text quality. And this is exactly why you can have something like Ask Kumuyi. Kumuyi is the general overseer of Deeper Life Bible Church. So there's an AI called Ask Kumuyi that has been trained on all the materials and the theology of Pastor Kumuyi. So if you ask it a question, it can give you context in like on how Pastor Kumuyi thinks like that. So this is the kind of thing happening there. So in summary, in this lesson, you learned how GPT works from ground up. So we studied tokenization, embeddings, positional embeddings, maxed self-attention, maxed self-attention so that the model doesn't see things in the future. It only sees things in the past. It uses things in the past to predict the present. It doesn't see the future. That's maxed self-attention. Then you have multi-head attention, which allows for many heads working together to get attention. Then feedword networks, residual connections, layer normalization, transformer blocks, cross-entropy loss, autoregressive text generation. So you also built a complete Tiny GPT implementation using PyTorch and trained it to generate text from a custom dataset. Although Tiny GPT is much smaller than GPT-2, GPT-3, or GPT-4, it contains the same fundamental architectural ideas that powers today's large language models. So GPT is an autoregressive. So our key takeaways: GPT is an autoregressive transformer decoder that predicts one token at a time, right? Then we have every input token is represented by the sum of a length token embedding and a positional embedding. So maxed multi-head self-attention allows each token to attend only to previous tokens, preserving causal language modeling. So it's not the you're not answering an exam question, having seen the question before getting into the exam hall. That's the idea of maxed multi-head self-attention. Then feed-forward networks transform token representations independently after attention. And you have residual networks and layer normalization, stabilizing the training of deep transformer networks. Then cross-entropy loss trains the model by maximizing the probability of the correct next token. And even a tiny GPT with only a few transformer blocks can learn meaningful statistical patterns from text, just like what we saw first, like first time. Then building GPT from scratch provides a deep understanding of the mathematical and computational foundations behind large language models. So if you want to really understand what is driving ChatGPT, this is a very good case for us here. Then we have our practice problems. Because so much time has been taken already, what do I do? Okay, well, I think I'm going to answer questions 9 and 13 here. So question 9 says a vocabulary contains 8,000 tokens and the embedding dimension is 256. What is the size of the embedding matrix? Then how many trainable parameters does the embedding layer contain? We're going to do that. So see all the questions from 1 to 10, you can see all of them here right now. Questions 1 to 10, all here. Then you can see 11. So I'm solving 13. Suppose the logits are 2.0, 1.0, 0.5. Compute the softmax probabilities. We've done this a couple of times. I will do that again. So see all this up to 14. Then see okay, can we see the rest now? We can see up to 19 here. Or can we see up to 20? So we can see 15 to 19 like this. And then 20. So let's go and quickly solve those two. I'll just be fast because this has taken a lot of time already. So let's go for problem 19. Problem 19. I mean problem 9 rather. Problem 9. Um, so a vocabulary. Okay, let me not write out the question to save time. So I'll just read it and just go ahead. A vocabulary contains 8,000 tokens, 8,000 tokens, and embedding dimension. So you have 256 embedding dimension, embedding dimension. So A is asking for the size. What is the size of the embedding matrix? So, so we need embedding matrix size, embedding matrix size. That's the first thing we need. Then B, we need the trainable parameters. How many trainable parameters does the embedding layer contain? So trainable parameters. So let me just shorten it this way. That's all we need here. So I'll just quickly go for that. Solution. So the vocabulary size is 8,000, like we already know. Then embedding dimension, D, is 256. So simply the embedding matrix has size, it has size 8,000 by 256. That's the embedding matrix dimension. Then on the other hand, we need that's A right there. So total number of trainable parameters. So the total number of trainable parameters is simply the same thing, is 8,000 multiplied by 256, which is 2,048,000. So there are 2,048,000 training parameters. So that's just straight to the point. So I go for problem 13 very fast. Problem 13. Problem 13 says, suppose the logits, suppose the logits are 2.0, 1.0, 0.5. So these are Z values now. So it says compute the softmax probabilities. Compute the softmax probabilities. That is straight to the point, especially since temperature is not added here. So I'll just go for the solution and say, we know the softmax function. The softmax function is this. Probability of I equals e raised power z I all over summation over j of e raised power z j, like that. So what that simply means is that we need we have we need all, so of course we have all our z's like that. We have all our z's. So we have z1 is 2 from what we have. So 2, so that means e raised power z1 is equal to e raised power 2, which is approximately 0.39. Then we have z2. Z2 is, this is 2.0. So z2 is 1. So that's e raised power z2, which is e raised power 1. And that is approximately 2.72. Then we have z3. Z3 is 0.5. So we have e raised power z3, which is e raised power 0.5, and that is approximately 1.65. With all of that in place, then we move on to compute the sum. So z1 plus z2 plus z3 is equal to 7.39 plus 2.72 plus 1.65, which is simply equal to 11.76. So with that in place, then we can compute the probabilities. So, P1 is 7.39 all over 11.76. That's approximately 0.63. Then P2 is 2.72 all over 11.76. That's approximately 0.23. And then we have P3. P3 is equal to 1.65 all over 11.76. That's approximately 0.14. Then with all of that in place, then we have we can then have our final results. If you can say thus, the softmax, the softmax probabilities, the softmax probabilities are 0.63, 0.23, 0.14. So it means that the first logit requires highest attention. So the highest attention should go to this. So the first logit requires highest attention. Highest attention. Like that. So the first token has the highest probability, so it is the most likely prediction, like that. So with this, we come to the end of this interesting video about making a tiny GPT. So you want to pay attention to that if you really want to know what's going on in ChatGPT and all of that. So let's look at the questions once again. So you have the questions 1 to 9 clearly here. Then you have, okay, let me leave that a little bit more. Then you have questions 10 to 13. So after questions 10 to 13, you have 14 to 18. 14 to 18. After 14 to 18, you then have the rest. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, question, what exactly are you waiting for? Why not go ahead and subscribe so you can always get alerted each time a new video is released, right? Subscribe and hit the notification bell rather, so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you special benefits you'll find out as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.